Well, hello everyone. My name is Mr. Naylor, and this is lesson 1.4 for Honors Calculus. Now, I want to pose a question for you to start today. And it's simply, what if y is not a function of x anymore? Now, you've had all summer to think about this, but what if y is not a function of x anymore? Does that mean that the sky is falling or that math isn't going to work anymore? Well, no, it actually means that instead, x and y will be functions of a third variable, t, which is called a parameter. Now, for some of you, you've heard of this before. You've heard of this idea of parameters and parametric equations. And for some of you, you have not heard of this before. And I just want to say it's okay. You're in the right place. There's going to be some things we do in this first chapter that some people have seen. There's going to be some things that some of you have not seen. In the end, we're going to work and we're going to get to the point that we all understand. So, a lot of things in math, students say, show me. What do you mean y is not a function of x anymore? What do you mean x and y are functions of a third variable called a parameter? And I'd like to show you, in fact, through a simple example where we have x equaling the square root of t and y equaling t. Now, what I've just shown you here is called a set of parametric equations. And it's not two equations, but rather it's one equation together. It's one set of equations. Now, the question really becomes, what is this? What's it going to graph like? What's the equation going to look like? How do we analyze this? And as a little bit of a pretest, I want to challenge you to see if you can do a little multiple choice and decide which one of these, we call them Cartesian equations, would actually be equivalent to this set of parametric equations. So in the first corner, we have y equals the square root of x. In the second corner, we have y equals x squared, a parabola. And in the third corner, we got y equals x, a nice linear line. So what do you think? Which one of those three Cartesian equations is going to be equivalent to these parametric equations? I'll give you 10 seconds to figure it out. All right, well, how many of you chose y equals the square root of x? No one. Oh, well, there's no one sitting in here. But had there been some students sitting in here, no doubt a few people might have put their hand up for y equals the square root of x. Now, we're not going to go over any reasons at this point. I just want to see what you think. How about y equals x squared, a parabola? Well, had there been some students in class, there would have been some hands that would have gone up for this one also. How about the last one, y equals x? Most likely nobody puts their hand up for that, which is good thinking because as we look at this equation, we definitely see something that's nonlinear. Maybe we don't know exactly how it converts or how it gets interpreted, but we see something nonlinear, and that last equation is a linear equation. All right, well, we're going to figure out which one of those three are correct. And to do so, let's do a little talking about some values. In fact, if we can go way back to the beginning to a table of values, I always like to tell students that a table of values is not babyish. In fact, a table of values begins to help you think numerically about these variables. And these variables are saying something. For example, they're saying that x is going to equal something involving t. It's going to equal the square root of t. It also says that y equals t, which means that these x's and y's are functions of t. T is kind of going to be inputted so that we can get an output. And that's exactly what a table of values does. Now you can see that this table of values has 3 columns. And so it would be nice if we could start to input some numbers. And my question would be for you, what kind of numbers do you want to input for t? Now there's a lot of numbers out there. There's positive numbers, there's negative numbers, there's big numbers and small numbers. So what kind of numbers could we plug in here for t? Well, observation would tell us that there's certain t-values that you can't plug in, and that would be negative t-values. Now, for this set of parametric equations, it has what we call an assumed parameter restriction, or an assumed parameter. Now, the assumed parameter would be that t is not allowed to be negative. So we can say that the t-values, in other words, the types of numbers we plug in, need to be positive. I'm going to write down the assumed parameter so that we can begin to create our table of values. Now, I could certainly plug in 0. I could also plug in 1, I could plug in 2. Let's stop there so we can see how to do it. Well, it's pretty easy because if I just plug in 0 for t, I have to think to myself, what's the square root of 0? We all know that that's 0. Well, that would be my x value. That would be my output. It turns out that if I plug 0 in for this t, then it'll give me a y value that's also 0. Now, if I plug in 1 for t, I'll get x equaling the square root of 1, which is 1. And we'll get y equaling, well, 1. Now, when I plug in 2, I'm going to get the square root of 2. Now, the square root of 2 is about 1.4, but we can write that down as the square root of 2. And we can also plug 2 in for t, and again, y equals t, so y equals 2. Now, I can continue to plug in any t values I want, but it can sometimes be wise to pick ones that are going to be perfect, that are going to have to be a perfect square so that they have an even square root. So a student might say, well, why don't we go ahead and plug in 4, and then maybe why don't we jump ahead and plug in 9? And I would say, good idea, because the square root of 4 comes out nicely to be 2. And now when I plug in 4 for this t value, I see that y equals 4. Go ahead and fill in the last line of our table if you haven't done so already. And you should have came up with 3 and 9. Now, just so you realize, the reason that we're making this table of values is so we can graph it. But to be able to graph it, we need to understand that there are still x and y points. And I mean literally or only x and y. And so when I go to graph this, I'm actually only using the outputs of my table. Notice I'm not going to graph my parameter. I'm not going to graph t. All right, well, let's make a graph. And just saying, as we make this graph, we need to be aware of our multiple choice because we're getting a little bit closer to which one is right. But for now, we're just making a sketch of each of these ordered pairs, 0, 0, 1, 1. Now the square root of 2 is 1.4, and the y value is 2. So we want to see that we begin to change in a non-linear fashion. Okay, now this would be my next ordered pair, 2, 4, which again, I want to kind of begin to show its position clearly as being not in a linear fashion, but as we may begin to see here a little bit more in a non-linear fashion. In fact, when you connect the dots, we are not on a straight line. So what are we? What are we? Are we y equals the square root of x? Well, no, okay, because that would be opening, that would be curving in a little different way. We've already said that we're not y equals x. So what about y equals x squared? Now, if I had students in class at this time, we would be pausing because there should be a little light bulb going off. And the light bulb should be telling you that, wait a minute, what I graphed over here, which by the way is the graph of our parametric equations, what I graphed over here is also not exactly this equation. Wait a minute, none of these are right? Well, one of them is almost right. And so what we want to understand is that this, which refers to these, is only half a parabola versus y equals x squared, which is a full parabola. Now, if you're wondering, okay, it sounds good, I get it, so what's the problem? Well, there's not a problem. It's more of an understanding that these equations, when converted to Cartesian, now let me stop right here, because if you're saying, whoa, what's Cartesian? Cartesian is the type of math you've grown up with, x and y. This is parametric. This is parametric because it has x, y, and t. Well, what I want to do is show you that we can take what's parametric and we can convert it to Cartesian. Now, how do we convert it to Cartesian? Well, by realizing that these two equations can be changed. They can be changed so that they are both equal to x. Now, when you square both sides of the first equation, you can say that x squared equals t. We already know that y equals t. And so we have a very easy conclusion here. If we have x squared equaling t, and if we have y equaling t, then by simple substitution, we're able to say that y equals x squared. Now remember, y equals x squared is almost right. Why is it almost right? This is half a parabola. This is a full parabola. So how do we say what's written here using Cartesian? Well, by using the comma. Now this is new math for many of us. The comma in math often refers to some type of restriction, some type of additional statement, something that also needs to be part of the answer. Right now my answer is a full parabola. What I need to do is say something so that I only get half a parabola. Now, what's the something that you need to say? You need to say that x needs to be greater than or equal to 0. Now, how do we get x greater than or equal to 0? Honestly, by observation. We see by observation that these x values in my table are greater than or equal to 0. We see by observation that this graph is only to the right. It's only the right half of parabola. So my correct answer is y equals x squared when x is greater than or equal to 0. Now, we did a couple things here. We basically analyzed these parametric equations by making a table of values, by making a graph. Now, there's something I want to add to this graph. I want to add what's known as the initial point. The initial point is pretty important because that's where my parametric equation starts, so I want to label it. We also have something on this graph known as direction. You may not have thought of it, but when I plot these points, the direction I plot them is that way. And so we put those little directional arrows on as part of our analysis. Then the last thing I did is I converted it. Now I converted it by using a little bit of substitution and a little bit of observation. Parametric equations. Let's take a step back and kind of think about what we have. You see, what we have are x and y now being described as a function of t. That means x is equal to something with t, and y is equal to something with t. And we also have this interval of t values, which isn't something you want to just brush over because the interval for this problem was assumed. Now, if you're saying, wait, how did we know it was greater than or equal to 0? Because those are the only kind of t values you can plug in. And so we have a certain interval of t values. Now, if you have that, then when you plug in t, you'll get an x, and when you plug in t, you'll get a y. And those points, those x and y points, well, they make your parametric graph. So, parametric equations are really just equations that now involve this parameter. They involve this extra variable. By the way, if you're already saying, well, why do I need this? Why do we need parametric? Why do we need t? Physics application, because often t involves time. And what ends up happening here is that we can have times that we could plug in to get x and y values, particularly with projectile motion. If something's moving in a projectile, we not only can know its position x and y, but we can know the time of that position, which would be t. So we have this third variable. These are just some statements that you can read. You can write them down. But ultimately, I'm trying to tell you that this is what I want you to start to think about with this idea of parametric equations. So have you gotten the idea? T is a parameter. Are you getting the idea that T actually determines what you're going to graph? You'll start to understand, but if I'm only going to be able to plug in these T values, I'm only going to get these X and Y values. I'm only going to get this half of graph. Okay. By the way, for this problem, not every problem is exactly like this, but T kind of tells all. T tells what portion you're going to graph. Now, T can be an open or closed interval. This is an open interval. It's an open interval because it keeps going in one direction. It basically goes to infinity. A closed interval would be if I'm between 2 points. And I could definitely have that situation also. And by the way, we could also have problems that have no interval restriction. And if there's no interval restriction, then it's open, but it's open the whole way from negative infinity all the way up to positive infinity. So what we want to do is not try to say that this is always what's going to happen with T. T could be open, it could be closed. All right. Always a good opportunity to look at another problem. We've done one. Let's look at another one. And you knew this was coming sooner than later. Since you already graduated from trigonometry, we now are allowed to use trig functions. By the way, you can also write parametric equations vertically. I can put x on top, I can put y on the bottom. They can also be written either way. So x equals the cosine of t, y equals the sine of t, and I'm going to have this statement written beside our parametric equations, where x is less than or equal to t is less than or equal to 2 pi. Oh, yes, I just said it, 2 pi. Now, some of us have had a little more exposure to this, some a little less. But the bottom line is, whenever you see pi with a trig problem, you have to understand that we're talking about radians. Okay, now, radians are just angles. It's just a different measurement of an angle. Why don't we see if we can come up with a table of values? Now, we make the table of values, just like before. We actually have 3 variables. But t is still my input variable. So I want to be thinking about what kind of t values I need to use. Now here's the good news. It tells you which ones to use, the ones between 0 and 2 pi. So it turns out that 0 would be guaranteed to be my initial point, and here's a new vocab word, but 2 pi is going to be my terminal point. 2 pi is going to be my last point. Now I just wonder, can you come up with some radians that might fit between 0 and 2 pi, using some prior knowledge? Pi would be a good one to use. It's right in the middle. Now, if you're really on the ball, you would say that we have also some radians that are between 0 and pi, like maybe pi over 2. And then the one between pi and 2 pi is 3 pi over 2. All right, let's plug these in. Now, we have students in class, a number of you would be getting your calculators out at this time. That's fine, because you understand that you could use a calculator to get this. What I want to do is I want to encourage us to think about the theory of trigonometry a little bit, so that we can further understand just what did we try to learn last year. Now, the theory of trigonometry goes back to, that's right, I love the unit circle. It goes back to the unit circle. Now, the unit circle is a really nice circle because it has easy to find coordinates. Since it has a radius of 1, it's very easy to find the 4 corners. I'm using that a little loosely because, of course, there's not really a corner on the circle. Now, in case you didn't get this last year, 0 radians is a rotation. And if I'm not going to rotate, then I'm going to be on this ray, or this terminal side. That's 0 radians. Now if I plug 0 into cosine and try to do the cosine of 0 without my calculator, all I'm doing is thinking about the x value at this point of intersection on the unit circle. And folks, it's that x value right there. It's the number 1. So when I write the number 1, I'm referring to the x value, that x value, at 0 radians. And again, 0 radians is just a rotation. You know what's going to happen when we plug 0 in for t here for the sine? So we do the sine of 0. That's right, that's going to be the y value. So the y value is sine. Now, pi over 2. Pi over 2 is the same as 90 degrees. If you forgot that, you can still use that right now. So pi over 2 is 90 degrees. If I plug pi over 2 into cosine, that's like looking for the x value right there, that x value. If I plug pi over 2 in for sine, for t, and do the sine of pi over 2, we're looking for the y value. Sine is y, cosine is x. It's simply a way to use points to match up with angles. Now, pi is an angle. You have to remember, or at this point understand, that to be at pi is to be at 180 degrees. Are you thinking about the cosine right here? The cosine? That's right, it would be -1. Are you thinking about the sine? That's right, it would be 0. If you haven't yet, I encourage you to try to fill in the rest of this parametric table. All right, so 3 pi over 2 is this rotation. It's the same as 270 degrees. This would be the x value, this would be the y value, and 2 pi is all the way back to the beginning. And so when I get back to the beginning, I'm actually repeating my same x and y values. All right, now, why did we do this? So we could get a graph. Sometimes students say, but you already have a graph, Mr. Naylor. Be careful, this was the unit circle. We used it to help us get these points. Now we're actually going to make a graph. I'm going to go ahead and get rid of this so we don't get confused, because now we're officially making a graph. Now it turns out when you start to plot these points that you actually are plotting the same points. But again, it just turns out. So when I plot these points, now something to realize at this time. The direction that these points are being plotted matters. I plotted this one first. It's the initial point. I plotted this one second. Well, the direction matters. There's always direction on a parametric graph. Okay? And as I continue to plot these points, I end up finding myself going all the way back to the same spot, which is also my terminal point. Now we always label the initial and terminal point. How do you label it? With words, and you always use directions. All right, now to do a parametric analysis, there's always this expectation to make a graph and to convert it. So to convert it is to start to think about anything you see from this graph that you remember, maybe from algebra. It's also to think about anything that you could do to these equations. Now you say, what do you mean that I could do to these equations? Well, is there anything you could do to these equations to end up getting rid of the letter t? Now when I say getting rid of the letter t, you can't just kind of like cross it out and say now it's gone. But you can do something to both sides of the equation that might get you into some fun and familiar territory. What am I talking about here? Well, I wonder if any of you have ever seen x squared and y squared in the context of, I'm sorry, check that, reset. I'm wondering if any of you have ever seen sine squared and cosine squared in the context of an identity. Now, doesn't that just sound kind of sweet? Doesn't that just sound sort of nice? What did I say again? Sine squared and cosine squared. Interesting. When you write them together, does it start to sound like something? Something from trigonometry, something like an identity. How about if I add them together? Isn't that the most beautiful identity you've ever heard? Sine squared plus cosine squared equals, say it together, sine squared plus cosine squared equals 1. Now, you say, Mr. Miller, what is going on here? I thought you were trying to get rid of the letter t. You wrote the letter t. That I did, because what's sine squared equal? Yes, it equals y squared. What's cosine squared equal? It equals x squared. Wait a minute, now I have y squared plus x squared equaling 1. Or often you'll see it written with x first. We can say that x squared plus y squared equals 1. Now, a little time out here, okay, because this is a lot of math for the first day, but it's pretty neat, isn't it? Because x squared plus y squared is the equation, x squared plus y squared is the equation for what? For a circle. It's the equation for a circle. Folks, that's exactly what we have right here. What I'm saying is that this is a fact from algebra. And if you never heard it, you can still believe it. That's a fact from algebra. X squared plus y squared is the equation for a circle. That's exactly what I have here, which is the equation for a circle with a radius of 1. You see, it's actually x squared plus y squared equals r squared. I'm going to convert the number 1 to a variable for a second. Okay, it's because r is the radius. And so my final answer is to give the radius, which was 1. But now we can say that x squared plus y squared equals 1 is equivalent to this graph and is equivalent to these parametric equations. Do I need a comma? Do I need something sort of beside my answer? Do I need to say, hey, x can only be positive, or y has to be, greater than or less? The answer is no, okay? Because my equations already create these points. And so I don't need to say something like that x has to be only a certain type of number, because the only type of x values I get are the ones that are given by, let me think about this a second. It would be redundant to go over here and say that x has to be maybe between -1 and 1, because that's already what is happening based on my equations. Okay, so I don't have to say that. It's already what's happening based on my equation. So I don't need a restriction for this one. Now this would officially end the first day of lesson 1.4. Now what we're going to do is the second day of lesson 1.4. And so if you're ready to continue with me, normally at this point, after students had 23 hours to take a break from math, actually, we never take a break from math, right? But you know what I mean. Students had a chance to take a break. The next thing I would ask them to do is to try to analyze these parametric equations. I would ask students to try to analyze these parametric equations. Now, these parametric equations would have, let me say that a little better. let's say that these parametric equations would have this restriction. And by the way, you don't need to come up with these restrictions. These are things that are part of the problem. These are things that are part of the given. But now what I want you to do is I want you to start to try to analyze it. Right? Now, if you want to try to do this on your own, you would take the plunge and you would start to make a table of values. Same table of that, same type of table that we made the last couple problems. If you want to make the plunge and do this on your own, you would start to list some t-values. Okay, just give a little pause. Now, did you use your restriction as your t-values? Well, I say to you, it's definitely a starting point. Right? It's definitely a starting point. I guarantee that's your initial point. I guarantee that's your terminal point. Now, if you're a little bit unsure about what to do in between here, I can understand. Sometimes students are a little unsure. Should they know about a number that would be in between 0 and pi over 2? I would say that you could know. In other words, it's definitely true that pi over 4 goes between 0 and pi over 2. But I'd like to show you how we can go through this problem without worrying about kind of that extra number. Because the numbers I showed you in the previous problem are always going to be those 4 corners. And the 4 corners are going to be enough for us to be able to analyze these problems. All right, now, did you plug in 0 for t? Okay, if you used your calculator, you could do the cosine of 0 and then multiply it by 2. If you use the unit circle, then you might be over here thinking about what's going on at 0. And of course, the same thing is always going on over here at 0. That's because it's always the same point. Bottom line is when you plug in 0, you end up getting 1. And then you're going to multiply it by 2. If I plug in 0 here for sine, I'm going to get 0, I'm going to multiply that by 2. Let's make sure if you're using your calculator that you're using it correctly, okay? Because it is actually another skill that's part of this, although I want you to be able to do it without your calculator. I also like you to know how to use your calculator. The main thing to remember here is that your calculator has a mode. Whether using a scientific calculator or a graphic calculator, in the mode menu, we each have degrees and we have radians. I want to make sure that I'm toggled